Thank you. Thank you for having me here. It's exciting. So I'll start with the customary disclaimer if my clicker starts working. One moment. Why is it refusing to work? Oh well. So opinions are my own, which is the usual thing, but also since I'm recently a freelance, they're also my employers. So please feel free to reach out if you enjoy any of whatever is going to happen here, or you want software development or workshops or whatever. So this is the disclaimer. Okay, so if you have been programming Scala for a while, you probably stumbled upon people trying to be too smart for their own good. In this case, they're expressing some complex invariants about a schema validation at the type level. And we'll get to the details later on, but whenever complex types appear, implicits are very quick to follow. And so you would encode this complicated type-level logic as an implicit computation and abuse implicits for the type-level stuff. And it might work, it might not, but when you actually try to run and check those schema validations, you might fail, and you get this completely opaque error showing you that it failed, but you have no idea why. What fields are incorrect, what's going on, how do you actually debug it? So you might have this implicit stack trace or something, but it's very difficult to actually figure out, and especially if as your computations become more and more complex, it's going to get nastier and probably not a reasonable thing to do. So this is not a very helpful error. And my claim for this talk is that in Scala 3 we can do better, and a lot better, hopefully. So we're going to take a look at the compile time error function, which is a new addition to Scala 3, which at first look might not seem particularly interesting, but it turns out that it can be very, very useful for the problem that I just described. And when mixed with the new type-level capabilities of Scala 3, which we'll review quickly as we go along, we can actually get some very developer-friendly custom errors that will hopefully solve the pain that I just described. As an example, I'll try to use something fairly realistic as something to actually see how this works out. You can say that we can do everything we're about to do here with macros, even in Scala 2. I won't be doing any macros here at all, for two reasons. One is because they're scary, but the second is they're not always that reusable, because sometimes you do a macro, it's something very one-off, and you can't really reuse it in other contexts. And the techniques I'm about to show you here are fairly general, and they're using standard language features and might be reused in other contexts as well. And since we don't have a lot of time, and probably will go overboard, as I usually do, this is not a tutorial. So all the details, you can find the full code in the repo I'll link to later. So, by the way, how many people are familiar with the movie This is Spinal Tap? Anyone? Like 2, 3, okay. Oh well. So the main issue here that we saw earlier is poor reporting, and our aim is to fix the reporting issue. So first, let's introduce the problem that we're about to solve. So we're representing a database schema using a case class, and the DBAs have some very, very strict requirements about what we can and cannot do with those schemas. And these are the requirements. They may seem a bit random, as if someone just made them up. This is not the case. So at most 25 fields in our schema, exactly one key field and exactly one timestamp field. I have no idea why the timestamp is so important, but they say, and I can't argue. Strings cannot be more than 500 characters, like abstracts in call for papers in conferences. And also all fields have to be prefixed with TR. Why? I don't know. Some legacy reasons. Now, it's been a while since I actually interacted with DBAs face-to-face, but how I imagine them is like that. And so I really, really don't want to mess around with the DBAs. So this gives me plenty of motivation to actually stick to the requirements, and better yet, do it at compile time so that nothing leaks into the production, into runtime. So to make the problem more concrete, here's the actual case class we'll be trying to validate. So we're modeling a hotel with all the various things that are relevant to hotels. And we can see we have some type safety here. We have dedicated types for key and timestamp. They should appear exactly once. We're trying to enforce the strings to have some certain size. But some of the requirements are not that easily enforceable in types. For example, how do you count the number of fields in the case class? Or how do you know about the TR prefix? So to implement the different requirements, we'll need something more sophisticated than just plain types in the case class. And that's where the error function is going to appear. So let's introduce the error function, the star of this show. So you import the compile time package, and you run this code. And if you try to execute the code, what you get here is a failure with the specific error that you specified. And this code wasn't running. It failed to compile now. So this is not a runtime error. It's a compilation error. So this is the power of the error function. It stops compilation with the message that you want to provide. So let's try to actually implement the requirements that we have. So the first requirement is that the size of the case class is not larger than some limit. So in this signature, we're taking some type, stands for the case class, a maximum size, and here we're using an implicit instance of a case class, which provides us compile time information about the case class. We'll get deeper into what exactly is there later on, but for now, just know that it's compile time information about the case class. So here's the implementation. Oh, the clicker is not working, sorry. So we're using an if here. We're looking at the size of the case class compared to the maximum size, and in case it's too big, we produce a compile time error. Notice here that we're using inlines. So inlines let the compiler evaluate at compile time certain conditions and logic. So in this case, the compiler can look at the statically known maximum size and compare it to the statically known size of the case class. And if it cannot do that, if it cannot compare at compile time, it will complain about it. But in this case, it actually works. So if we try to compile our case class, we check the number of fields, and we see that indeed there are too many fields here, and we get a compilation error, and it just stopped compilation. So this is nice, that fulfills the requirement, but it's not as useful as it might be potentially, because we don't have any extra info here. For example, what was the actual number of fields in the case class, or what was the limit? And so since we're aiming for developer friendliness, let's try to improve on that and make it more developer friendly. So here's a second attempt to do that. So we're doing pretty much the same thing, but now we're creating a longer error message, and we include here the size and the max size for the extra friendliness. And we compile it, and it fails to compile. But in this case, for the wrong reason. It's not the failure with the case class, it's failure to invoke the error function. And it complains that it has something too complicated to compile. And this makes sense, because we're trying, the error function is going to be invoked at compile time, so it has to evaluate its own argument. And since it's not a macro, it cannot just generally do anything with whatever arguments. It's pretty much limited to literal strings. And here we have a conversion from int to string, which we have to apply, which is something that the compiler doesn't support natively and cannot do at compile time. So the error function is quite limited to string constants. So the full rules are a bit more complicated. So you can either use compile time constant strings, or you can use strings separated by the plus operator on strings. So the first example is okay, but the second one, since there are only pluses here, the second one is bad because you have both string interpolation, which is a complex method, and a plus with an int, which requires a conversion. So this might seem very, very limiting. Where do we get all those compile time constants? And how can we make it sufficiently expressive so that we can actually provide those user-friendly, developer-friendly errors? So there are three main sources for compile time constants. So literals, like we've seen before, they're not that interesting, so we skip those. There are inline definitions, which the compiler can evaluate at compile time and actually splice them in as constants. And given that inlines can be recursive as well, this can be quite a powerful technique to actually do complex computation, but it might get quite cumbersome if you try to scale it out. And which leads us to the third option, the const value function. It's another function from the compile time package. it takes as an argument a singleton type or a literal type and produces a compile time constant that matches a value that matches that type. So for example, we have the type, literal type ABC, and we assign it to a type alias, and we do const value on that, and we get a string literal ABC. And the second example, we have a literal integer type, and then we apply the type level function to it, to a string, which is built into the compiler, and we get another constant, in this case, another string, which is a compile time constant. So this is the first step. This is what we need to actually embed numbers, in this case, into our error messages. And because the type level techniques in Scala are quite powerful, this will also scale to the full use case that we're about to describe. So let's see, let's try to use this. So we change the signature again. Now we take the int as a type parameter rather than a value, and we do pretty much the same thing, but we use the const value call to apply to the size of the case class as a type and the size, max size as a type as well. We then do the comparison. Since these are converted by the compiler into actual constants, then the compiler can do this comparison, and then we produce the error message. In this case, we're using const value and the toString call type level function to convert our size and max size to actual literal constant strings that the compiler can evaluate, and then it's only separated by process, so that's okay. And if we compile it now, we get a very nice, helpful message that contains all the information that we want. It's kind of a shame that we don't have any string interpolation, but that's okay. So the error function is useful for simple static errors, but as we just saw, this might be a bit cumbersome if you want to scale it out to something more complex than just fixed messages. And taking it to the type level, and we just saw a hint of how we can do that, can actually help us scale this out into the full developer-friendly error messages that we want to produce. So now we'll take a deeper dive into type level computation to achieve this goal. Sorry. So let's make a quick review of Scala's type level capabilities. I'm not implying anything here. It's just a quote. You don't have to take it seriously in any way. So Scala has many type level features. Match types, recursive types, singleton types, arbitrary size tuples, type lambdas, and whatever, many more. And it can be very easy to get lost in such a wealth of features. But what's important for our purposes is those features form kind of a this type level machinery forms a small type level language that we can actually use as a small language embedded inside the compiler. And we're going to use that language to produce our error messages. So let's see, so instead of going deeper into the actual mechanics, let's just see an example of how we can use the type level language to actually achieve something useful. So we're going to start with a value level example, and I'll translate it to the type level language step by step. So we start with a simple list of values, of integers. We have a naive implementation of the mem function using simple recursion over the list structure. We then do some transformations with anonymous functions, with map and filter, nothing very surprising, and we fold the result into a single thing which we concatenate one by one. So now we can try to translate this fairly straightforward functional code that most Scala developers probably seen to some degree somewhere into the type level equivalent. So the first step is that defs become types, and types usually are named with the upper letter. So we replace everything with type and uppercase. Then lists become tuples. So and notice now that these are not values; these are literal types of integer, and we have a tuple with 4 different types, each corresponding to an integer. Now the arguments to functions now become type arguments to the type constructors that we're using here. And so instead of a list, we're taking a tuple, and instead of the function, we're taking the type constructor. So in a sense, a type constructor is a function from types to types. Next, because match types let us do recursion over types, then this recursive call becomes pretty much the same thing. So pattern match on the tuple. If you have an empty one, we'll produce an empty, and if you have a head and a tail, we'll do the recursive call and apply the function f over our argument. Next, we want to apply our map over the list. So we use anonymous functions at the type level. So this special error here is type lambda that takes a type and produces a new one. And the plus operator here is a built-in compile time operation that works on types, takes type literals and lets us use them as if they are values at the type level. So we have two nice collection-like methods, map and filter, that we can apply to our tuple at compile time at the type level. And lastly, we have the fold call. So it uses, again, an anonymous function with 2 arguments. It looks pretty much the same thing as the original fold, just uppercase letters, but it's pretty much OK. And we can run this thing. So we take the result type, convert it to a value, and have a string. And this is a value that we can actually now use in the error function and evaluate it at compile time. So this will be our way of doing sophisticated logic while generating the error messages. So this is our type language, type level language. We have tuples instead of lists, pattern matching, recursion, and anonymous functions. So all the ingredients you need to do simple to use a simple functional language. It does tend to be a bit loosely typed because we usually just use plain tuples without any further constraints. You can think of Scala at the type level as a dynamic language, sort of, which sounds ironic, but that's the case. And so, as like many things in the Scala language, sometimes are quirky but serviceable. This is the case for this kind of semi-language. And it's very, and we don't have any string interpolation, which is kind of like Scala back in the day. And hopefully someone will come up with SIP11 re-implemented at the type level for the next iteration of this conference or something, and I can have nicer code. So now that we have all the groundwork laid out, we're finally ready to implement all the requirements in their full glory. We're going to pair up type-level computation with the error function and really take it up to 11, just like in this quote. By the way, the film is very, very nice. You're more than welcome to watch it. OK. So before we can produce any error messages, let's take a look at the inputs we're actually going to use. Before we saw the case class tab. So now we can actually see what it's made of. So basically, it contains metadata about our case class. So it's a tuple full of descriptors about each field. If you're familiar with mirror, we saw something about mirrors in one of the previous talks. It's pretty much the same thing, just restructured in a way that's more convenient for this use case. But the important thing is this is a tuple, and we can apply all our type-level functional programming approach to this tuple and convert it into the error message if so required. So now we'll write a small framework, so to speak, for type-level validation that we're going to use. So the first ingredient is the check type. So it's basically a wrapper around the function that takes a tuple. So again, we're loosely typed. We're just taking a tuple of whatever, and it's supposed to be the field names of the case class. And it's possible to be more principled about types here, but it gets cumbersome quite quickly, so we won't be doing it. So we have a couple of helpers. One is an error of a single message. It's a singleton tuple with one message, or no errors, which is the empty tuple. So the idea here is we're going to represent error messages as tuples, which are going to grow, and we're going to accumulate errors as we go along. Or if we have an empty list, an empty tuple, then everything is correct. And to make it a bit more convenient to use, we're defining a small helper called or_fail with. So it takes a Boolean type and an error message. If the condition holds, it produces OK. Otherwise, it produces a single error message. We're sort of aiming for a small kind of domain-specific language for validation at the type level. And to apply check, what we do is we take some fields, we take a check, and then we extract the check itself, the type constructor, and apply it to the fields. And the result is supposed to be either 0 or 1 errors. And so if you're familiar with validation from other functional libraries, so it's basically type-level equivalent of validation of a non-empty list of string and unit. We're just doing it at the type level, as we should do most things. So now with this framework laid out, we can actually implement our constraints. So here's the first signature. So we're going to do the most number of fields. So we take a max size parameter, and we implement a check that given some fields is going to produce something. So we're going to compare, so since this is a tuple, it has a size, we're going to compare the size of the tuple with the max size. This is a built-in operator in the Scala compile time package that lets you compare integers at the type level. If the condition doesn't hold, we produce an error message. So it's a bit cumbersome because there's no string interpolation, but it's fairly readable. The intent of the code should be quite clear that what we're trying to achieve here, despite being at the type level, and we can sort of run it at compile time. So by getting a case class instance for our type, we're applying the check once for the with 30, once with 20, and in the first case we have no errors, so an empty tuple. In the second case, we get this nice error message as a one-element tuple at compile time that has all the info that we want. So this is one check done. We can now move on to the second one. So it wasn't that bad. We probably can just swoosh through all the other checks quickly, which I'll have to probably do because I have no time. So next check is that it checks whether we have a specific type only once in the case class. Unfortunately, we have to take both the type and the type name because there's no built-in way to convert arbitrary types to their string names. Which is unfortunate, but so again, we're going to implement it by applying some functions to the tuple. So in this case, we're collecting all the fields of a certain type. We'll see in a moment the definition of this thing. If the result is an empty tuple, so we don't have any instances of the specified type, then we produce that an error that we're missing this type completely because we have to have it exactly once. If you have it once, then everything is okay. If you have it more than once, then we produce a very detailed error message where we say everything we know about this problem. So here we're really going for developer friendliness. So both the size and we have a helper function to render the field list that are actually duplicate instances of the same type. And so it should be fairly readable and nice. And so so here are the helper functions. So collecting is just a filter, checks that the field is a subtype of a certain type. So it's like a small functional language code. And here we use the equivalent of mkey string from collections on the tuple to collect all the field names into a single list of a single string with all the field names. And so these are the two checks that we need to provide here. So exactly one key, exactly one timestamp. Unfortunately, we have to duplicate the name of the type as a string. That's currently I don't see a way to circumvent it, but otherwise it's quite readable. Three checks down, so two more to go. So the other checks are per field checks, so meaning that we have to apply the same check over each field separately. So to make it easier, we'll do another bit of framework code. So we're going to apply a single check per field check over all the fields of a tuple. So we're basically applying this check to a single field, and then we concatenate all the results using flatmap into a single list of errors, in case they're there. Applying a check to a single field, what we're doing is we're applying the check, and then we render the error for that field. And this is what we're doing here is we're taking the field name and adding it to the error because we want our developers to actually know where the error came from. So this is, again, we're going for usability. So for the last two checks, and again, a signature. So we're taking at most max size for strings, and then we're doing a check all fields. So we're going to apply this check to all the fields separately. So given a single field, we're going to extract the field type. And then if it's a size string and n is larger than the limit, then we produce an error, an error that it's too large. And remember that we're going to render it with the field name, so we're going to know exactly where that came from. If we have a string, then we just forbid it completely because we don't want unbounded strings, and otherwise everything is okay. And the last check to implement is, so for some legacy reason, we have to have a prefix for our fields. So again, it's a per field check, and we're using the built-in matches function from the compile time package that takes a regular expression and applies it to a string. So we take the field name and the prefix that we're trying to check and run the matches function. So this is an important moment here that implementing matches on your own would be probably near impossible to do it. And if it wasn't built into the compiler, we probably won't be able to be as expressive. So we're basically limited by what the compiler is providing us in what we can do. And it would be really nice if there was some extensible mechanism to actually add more type-level functions without waiting for a new version of the compiler. But as it is, there are quite a few building blocks already in the compiler, which we saw before, the addition, comparison, and stuff like that. So we can do quite a bit. So matches is there. So that's it. That's the last check. So we can now collect all those checks into one one single validation kind of schema. So we start with an empty tuple of checks, and then we're going to add them one by one. So we have at most 25 fields, exactly one of key and timestamp. Strings are at most 500, and all fields have the prefix tr. And that's pretty much the description of all we want to do in a concise kind of type level way, just like on the first slide. But the difference will be that when we run it, we'll get nicer errors. So to actually be able to run this, we need one last ingredient, is the kind of the runner of our framework. So checkall is going to take all the fields of the class, all the checks that we have, and then apply each check and concatenate the results into one single tuple of errors from all the checks together. And then, because in the end, if there are errors, we want to render them, so we'll produce a nice string, and we'll also put them line by line, because we don't want like long input with one single string with all the errors. And to make an extra flourish, we're adding kind of a dash before each error, just to make it nicer. So make lines just creates one big string with new lines and dashes. And finally, we're ready to come back to the star of the show, the error function. So we're finally back at the value level. So this is a regular def, which is running at the value level. So we're going to tie the type level with the value level into a single definition. So we take a tuple of checks, so the tuple here, and we require a case class instance for it. And so we then apply all the checks as a type. But then now we have a type, a possibly empty tuple or a non-empty tuple of errors, and we have to do a value level decision over this tuple. And so the question is, how do we go back from the type level down to the value level? Luckily, there's a built-in function for it called erased value, which lets us, which creates a dummy value from a type that we can match on. We can't use that value, but we can just deduce its type and use it. And so in case we have an empty tuple, everything's okay, so no failures and everything is fine. But in case we have an error, we render the error list using the render function, and then we use the const value to drop it down back from the type level as a string into a string constant that error can use and produce the error, and which should abort compilation, and we're done. That's it. Are you excited? No? Okay, so this is the moment of truth. Will it work? So we're going to perform our checks over the hotel table class with the schema OK list of checks, and we're going to run it, and nothing happens. Which is okay, because hotel table is a valid schema and everything's fine. So it compiles fine as expected. We tested the first branch. So here's another case. Here's the suspiciously named bed hotel table. And do you feel the tension? Do you think it's going to work? Am I going to fail live on camera in my presentation? Look at that. What a lovely error. We have all the information here. I was so excited to get it first time. So all the fields are specified. Thank you. So we got all the information we wanted. We stuffed it into an error message. If you want to add something else, we probably could do it as well, because the framework is quite flexible. And so I find it very, very, very heartwarming. And also, even the DBAs are happy with that. So, and if they're happy, I mean, we're truly done. So. So we saw that despite the humble name, the error function is quite powerful. So you can start simple with fixed strings, but you can also go all the way up to 11 by using by harnessing the functional language at the type level. Notice that in the past we would probably use some Prolog-like implicit stuff. Now we're using a simplified functional language, which might be nicer in some use cases. I still like Prolog, by the way. Don't think otherwise. But still, our compile time capabilities with this new functional language are almost endless, which is very nice. And with about 100 lines of fairly reusable code, and I find it also kind of quite readable once you get used to all the upper capital letters on the methods and stuff. You get something that you can reuse and apply, and it's quite flexible and can do lots of validation. I actually was surprised myself how readable the end result was. I wasn't expecting that at first. And so custom compile time errors is something now that any developer can craft, probably, and you can delight your fellow developers with beautiful developer-friendly errors, all the while enforcing complex invariants where they belong, at compile time. And this is some very exciting uncharted territory, which can come with some rough edges. Not everything might work exactly as you might expect it to, and you can see the full details of this code in the repo. But still, it's very nice to work with, and I really hope this talk inspires you to actually explore a bit the error function and the type level capabilities of Scala 3. And you can find the full presentation here at GitHub, and reach out if you want anything, whatever, especially software development services or talks. And so that's it. Thank you.
Thank you so much, Daniel.